end the talk portion and move into the discussion portion. So who is leading the discussion? Marcella. Okay.
Shall I show the slides, Cindy? Yeah, please. So we thought of putting together a few questions that we would like to pose to you, which synthesize a little bit in simple form issues that have been brought up through the talks. And we had actually 3 sets. And we would like in particular to propose, because there might be too much otherwise, that we focus on the first one.
Right, and I would say as a slight further explanation of that, I think what we'd like to do is really focus on physical mechanisms, because we heard a lot about correlations and observations, and I think what we think is interesting is interpretation. So what do you really think is going on is what we'd like to hear. So shall we open it to comments?
So how do we proceed with the microphones? Because we have 2. Sandy, you hold yours, and I go around. Okay.
So here's a question to Robert Feldman. If I understood your talk, what you're saying is that the galaxies that quenched were in lower than average density environments, and they therefore were starved. That wasn't true for all of them, but it's, as you said, it's not a sufficient, but it's a necessary condition. And the ones that were still forming stars were in the higher density environments. Now the question is, how does this square with age matching? We know that at redshift 0, if you put galaxies that, if you assume that the red galaxies occupy high concentration halos, which correspond to the ones that are very low accreting at low redshift, and you put the blue galaxies in the low concentration halos, i.e. the ones that are still accreting, it's exactly the opposite of what you'd expect if the galaxies, I mean, it's also well known that concentration correlates with density. High concentration is high density, low concentration is low density. So it looks like your scheme would lead to exactly the wrong location today. Any comments?
All right, so maybe 2 comments. First, of course, I can't really say where these galaxies would be at redshift 0 because I don't have the simulations run down forward.
But you can run the simulation forward just with dark matter.
Yes, and this I did. So I think I could address this more carefully, but I think my feeling, that's more feeling to, well, as an answer to your question is, one has to be very careful by comparing average properties of galaxies to essentially the differences if you look at, at different quartiles. So here, the idea is that you have galaxies that live in maybe underdense environments. They collapse early, so they are high density peaks which are surrounded by a low density other environment. So they grow fast early on. They are compact, so probably they're more compact. Actually, well, looked at the sizes. I didn't have time to show it, but what the quiescent galaxies are more compact than the star-forming ones of the same stellar mass. So they're more compact. Their dark matter distribution is also more compact, but they seem to prefer to reside in essentially an environment which is then on average kind of lower density, so that the accretion shuts down. So I don't think that there is necessarily a disagreement with the age matching, because indeed these are the more concentrated galaxies.
Why don't I give this to Mark here? Here you go, Mark.
Okay, I would like to talk a little about the dwarfs, and I wanted to put together a few of the talks. So we saw, all right, so I mean, a few things interesting to put together. So Robert put up this sort of cold baryon mass versus halo mass, and it was an important point that dwarfs don't have less baryons, they just have fewer stars, right? So you need to sort of retain the gas without blowing it out. When they quench, it seems to be not by starvation, it seems to be environmental. That was Sean's talk, and then John sort of put together a mechanism, John proposed a mechanism for quenching without ejecting the gas. So, can we, and I'll throw in one more observational fact, which is that you only see quenched dwarves inside inside group environments, right? If you go look in the field, dwarves are never quenched. So, is there a consistent picture? And I mean, that's, yes.
We have to be careful. What Robert showed was that redshift 2 and higher. And we know that if we go to the dwarf galaxy today and you look at the total baryonic content in the dwarf galaxy, it is lower than in the more massive.
Is that true of field dwarfs as opposed to dwarfs in the local group? You have to be careful.
It depends on how what you call dwarf, but if you go down to 10 to the 9 solar masses and stars, for those galaxies it's definitely true. Below that it becomes tricky because we don't have too many.
And that's based on what?
Baryon to efficient relation.
I mean, they still lost 90% of those values, they just didn't lose 99%.
Okay.
I was surprised to see that redshift 2 apparently it's still not the case. Apparently we still have a lot of the cold gas sitting in this thing. It's not the same as redshift 0.
Yeah, one of the puzzling problems of quenching which I encounter are these transitions from blue to red nuggets. In the sense that you basically increase the rotation velocity in the very center, and make basically, this is what we call with the kappa quenching, in the sense that because of the change in the rotation velocities in the bulge region, you bring up basically the kappa value, and then you basically go above Q equal 1, and that is the way how we explain the quenching of compactified galaxies. Kappa goes up. That is epicyclic frequency. That is the idea behind that. The problem which I see is that if you look at Reinhardt's high redshift galaxies, there's still a lot of gas and molecular gas in the very center. So the only way you can make star formation go to zero is by keeping the kappa high, but you also have to keep the velocity dispersion high. Because if the velocity dispersion goes to zero, then the 2-Q parameter is zero. And you would still form a lot of stars in the very center. Now, to keep the velocity dispersion high, you need a mechanism to drive turbulence in the center. And I don't know how you drive turbulence in the center if you have shut off the star formation. So for me, the transition from the blue nuggets to the red nuggets, with all of this molecular gas still being around, is a problem. And I don't understand how you solve it. Reinhardt observes high velocity dispersions in the very center, but I don't really know what drives this high velocity dispersion.
Are you saying red nuggets have molecular gas?
Yes?
Fully quenched?
Well, Reinhardt can say a little more about this. These are the galaxies where we see no star formation in the center anymore. But it's not because they are got rid of the gas. The molecular gas is still around. It's because the kappa is high and the velocity dispersion is high.
Let me just ask for a clarification on the
Yes.
observations. What Guillermo is plotting is total star formation. So I would be focusing, if I use the term red nugget, on a galaxy which globally is not making very many stars. Is that the kind of galaxy you're talking about? With lots of molecular gas in the middle?
Yeah, exactly. So red nugget is kind of confusing. Red nugget could mean that you have no gas left and it's only stars and they are old. And it could mean that you have a lot of gas left and somehow the star formation is not happening because 2Q is much larger than 1. Yeah.
But I find this confusing because red nugget has been used observationally just to say that people find these quenched objects very compact and they're quenched and there is no ambiguity that they are, even spectroscopically. So I would keep that terminology to indicate these objects and I wouldn't confuse the picture.
Oh, maybe we ask Reinhardt to tell us about the molecular gas content of these quenched objects.
I don't think yet. No, I mean, I think, we can certainly take the star formation rate, use our scaling relationships, but that's a little dangerous, I would say. On the other hand, direct observations are very hard. I would say we have currently maybe, Linda, what do you would say, 10 objects at redshift 2 below the main sequence. So,
But just...
and the trend is the gas fractions go down and the depletion timescales go up.
But the gas is still there. It's not such that we have no molecular gas in the center.
Yeah.
And there's enough to form a lot of...
Right.
But again, the resolution is show that a CO sits at the place where they're not.
Yeah, so this, Frank, is, I think this is why I'm very careful here not to say too much. I mean, I think you can do these scaling relations, and so then you can make a statement, but you allow me to, or you would? I worry about the fact that in very concentrated regions, very concentrated star-forming regions in the local universe, the optical band has in the past given us all the wrong information, in the sense that the extinction is so large that you just cannot reproduce, so to speak, the de-extincted, extinction-corrected world anymore. That's why a ULERG you cannot study with H-alpha. You cannot, because you have to correct for a factor of 10 to 100, which you cannot. So I would wait on this until we really truly have millimeter, submillimeter based information on the gas content and the star formation rate in the nuclear region. So that means, interferometry in these galaxies, and that hard business.
I want to address Andy's issue from the theoretical point of view, and what again we see in our simulations is very simple. And I'm talking about the inner part, not the outer part. And I call it red nugget, with your permission, even if it's naked or not naked. So this compaction event makes the three parameters go in the right direction of quenching. Kappa goes up because you build up a core and the potential is deep. Sigma, the turbulence, goes up, maybe because of supernova feedback, maybe because of the compaction itself. No. Immediately after, I'm talking immediately after the end of the compaction, there's still a star formation, it's going steeply down. You still form stars, the compaction itself, as in our paper, brings sigma up, but also, as John Forbes, in his paper from a couple of years ago showed, the evolution of the disk is to make a hole, so you deplete the gas. And in anticipating simulations, the gas surface goes down. So the three parameters go in the right direction to make the Q parameter high and end up with quenching in the middle, and you get rid of the gas. Depletion is the most. Now, AGN feedback may help you do it even faster.
Let's not always hear from the same people. Anybody else has a question?
Just a quick comment on the red nugget and the galaxies below the main sequence. I guess that we should have a look at these galaxies, just following on Sandy's comment that traditionally what people have called red nuggets are as tiny red things that are fully quenched. And I think, I haven't looked at the pictures, but I guess some of your galaxies below the main sequence, they still have some star formation. They're below the main sequence, they're not fully quenched. So they may have a dense center, a dense core, and some star formation, and some gas in the ring. So it's not inconsistent, it's this, they're not the same thing. The other question would be, what are the progenitors of the red nuggets with no disks, no gas around them? But those, the ones that you said, obviously exist.
I'd like to ask another question of Reinhard. So there was a big discussion at coffee among some of us about, in the compactification event, what would happen in the exterior part of the galaxy? Would the star formation be killed far out or not? And what do we actually see? So I have another observational question for you. Since you do have measurements of H-alpha, is your H-alpha more extended?
Yeah, actually, so we have about 35 data sets now on what you would call compactified galaxies with the parameters greater than 10.3 or whatever. And most of them, I think 33, are rotating galaxies. Okay, so whatever.
I'm more interested in the radial extent.
Well, that already tells you that they're bigger. in H alpha, because if there were 1 kiloparsec radius rotators, and then there's an edge, so to speak, we would not be seeing limited data in KMOS 3D, see nice rotation patterns. So it tells you there must be H alpha on a larger scale than in the optical continuum.
So if I may add to this, the same story comes out from this SYNF project that actually also Rena showed yesterday, but also the Takel et al. Paper that I showed today is based on the same sample, together with Reinhard, Linda, and Natasha, and so on. And there the point is indeed that there is this ring of star formation in the outskirts, which both Reinhard has pointed out in a paper 2 years ago, and we emphasized that on the Takel et al. Paper.
So if I can return to Andy's question, I think the primary quenching mechanism is getting rid of the gas. But then you do ask a question of, are there situations where we see molecular gas with a long depletion time? And in the local universe, I'd say we have 2 examples of that. One is molecular gas in early type galaxies. So some early type galaxies have molecular gas disks with long depletion times. And it turns out that's just because they're very puffy. And if you actually measure the ratio of the depletion time to the free fall time in those galaxies, and this is Tim Davis's paper, it's the same as everywhere else. It's just that because the gas is puffy, it's got a big free fall time. In our galactic center, we do see molecular gas that isn't forming stars as fast as you'd expect. And that's probably because Q is much greater than 1, it's gravitationally stable. And there is a potential mechanism, which is once you've formed a galactic bar, there are instabilities associated with the bar. Basically, the bar drives an acoustic instability in the gas, so that even if you have no star formation, you can maintain a very high velocity dispersion, and what's powering it is the gravity of the stellar bar.
Could I ask actually a question about this, given that we are going into this direction? The Rodriguero et al. Work, and other people I suspect, shows that at redshift 2, we have something like 10% of the star formation rate going on this very molecularly obscured objects, and the 90% is on them in sequence. And in terms of stellar mass, we have a 2%. So are you in some way saying that this 2% is what we should be focusing on rather than the 98% that seems to be taking place at redshift 2 on the main sequence?
Okay, I'm not quite sure how you got that from what I said.
You catch up on what Andy was saying, and the emphasis, and Reinhard was saying how we should be carefully interpreting what we see in terms of the optical. And the point is that when we go to the infrared and we see how much of the star formation happens in the universe at redshift 2, the budget is really down to the main sequence, not to the very obscured objects that Herschel finds out. So do we think that every galaxy goes through that phase, so we need to understand that phase, or do we simply see there is a small fraction of the galaxies that are there and we can just study the bulk?
I don't know about the demographics. I'm just saying that there are examples I'm not making any statement about demographics. I was simply asserting that there are very few, but there are examples in the local universe of molecular gas without much star formation, where the depletion time is very long. And so it wouldn't necessarily be totally surprising if we found a few examples like that in the high redshift universe too. They're rare, they're not the bulk of galaxies, but they exist and we can understand them.
So I'm curious, that's because this molecular clouds off the plane with some angle with a stellar disk. What's the physical difference between regular molecular cloud?
Between regular molecular clouds and ones that aren't forming stars very much?
Right.
I guess I distinguish the 2 cases of galactic centers and early type galaxies. So in the early type galaxies, the star formation rate is actually respectable. It's just that there's a very high surface density of molecular gas, and the star formation rate isn't as high as you would expect from that surface density of molecular gas. And I'd say the reason is because if you see that surface density of molecular gas in a Milky Way-like galaxy, it's in a very thin layer. And if you see that same thing in an early type galaxy, it's in a much thicker layer. And I think if the velocity dispersion is large, some of it's off plane, maybe the density isn't as high as you'd expect. If you see a surface density of 10 to the 3 solar masses per square parsec of molecular gas in, a disky galaxy, it's usually at a density of 10 to the 4 or 10 to the 5. If you see it in an early type, it could be at a density of only 10 to the 2 or 10 to the 3. Now, that's very different from the galactic center molecular clouds, which are really distinguished by the fact that they are very, very turbulent for their mass. They're probably super virial.
Yeah. I just to point this out, the assumption is that usually the tumor Q is much larger than 1, and therefore even if you have molecular gas that could form stars, it's not self-gravitating. That's the idea. But a high tumor Q requires a high dispersion, turbulent velocity. And the high turbulent velocity requires a source of energy. And if you do not have star formation, shut it off, what is then the source of energy? That's what I ask. And and of course, Mark says it's by whatever irregular motion due to a bar or whatever. Yeah. But you need to find an energy source, and that's the main problem.
There is an instability which you can show exists near our galactic center, and generically should exist in many galactic centers where there's a bar.
So that would mean that maybe all the red nuggets go through bar phase, maybe, or whatever.
Maybe I don't know, but I can say for local galaxies, where there's a bar, there will be an unstable region in the center.
Okay, we think we should change topics.
No, actually, the discussion is over, I think. That topic is lunch.
Okay.
What was your other topic?
I was just going to...
I was going to make an announcement before we quit, but...
I know we're getting to the end. I just wondered if there were any other people who wanted to raise another point before we break. I guess not. All right. Thank you all.
Just a couple of quick procedural comments. First of all, if you have...
A little bit in simple form, issues that have been brought up through the talks. And we had actually 3 sets. And we would like in particular to propose, because there might be too much otherwise, that we focus on the first one.
Right, and I would say, as a slight further explanation of that, I think what we'd like to do is really focus on physical mechanisms, because we heard a lot about correlations and observations, and I think what we think is interesting is interpretation. So what do you really think is going on is what we'd like to hear. So shall we open it to comments?
So how do we proceed with the microphones? Because we have 2.
End the talk portion and move into the discussion portion. So who is leading the discussion? Marcella. Okay.
Shall I show the slides, Cindy? Yeah, please. So we thought of putting together a few questions that we would like to pose to you, which Cynthia, you hold yours, and I go around. Okay.
So here's a question to Robert Feldman. If I understood your talk, what you're saying is that the galaxies that quenched were in lower than average density environments, and they therefore were starved. That wasn't true for all of them, but it's, as you said, it's not a sufficient, but it's a necessary condition. And the ones that were still forming stars were in the higher density environments. Now the question is, how does this square with age matching? We know that at redshift 0, if you put galaxies that, if you assume that the red galaxies occupy high concentration halos, which correspond to the ones that are very low accreting at low redshift, and you put the blue galaxies in the low concentration halos, i.e. the ones that are still accreting, it's exactly the opposite